Okay, geometry students, I appreciate you finding time to get your notes taken care of. I believe these will be the notes for Tuesday or possibly Wednesday's class. I'll know a little bit more tomorrow on Monday in class. But at any rate, these will either be the notes for Tuesday, November the 4th, or Wednesday, November the 5th. Our objective for this day will be the student will learn the definition for congruent polygons and discover the properties that accompany that definition. You can leave the date blank on your notes for right now until we're sure what day these will actually be for. Okay, but at any rate, copy down your objective, and as always, press pause anytime you need more time to copy something down, and then press play when you're ready to move on. Now, the definition for congruent polygons is actually one that a lot of people have come to high school from junior high with. And one of the first things that we did at the beginning of the school year is we came up with a definition for the word congruent. And what a lot of people said was that congruent meant same size, same shape. And we said, no, that's going to be something else. The word congruent simply means equal measure. So what is it that is the same size, same shape? That is actually the definition for congruent polygons. So that's what we're looking at today. So as we have learned in previous years, the term congruent polygons means same size, same shape. However, just like everything else that we've seen in geometry this year, the same size, same shape idea, there must be something that causes that to happen. There must be specific reasons that two polygons would be the same size. Two things that must, or something that must happen in order for two polygons to be the same shape. Okay, so there must be something that causes two shapes to have the same size and the same shape. And just like anything else this year, you cannot simply eyeball it, say that you can tell that they're going to be the same size and same shape. That's simply not good enough. So let's look at what it's actually going to take for us to decide that two polygons are congruent. Those two things are, first off, corresponding angles must be congruent. That's going to be a requirement for two polygons to be congruent. The corresponding angles must be congruent. This is actually what is going to cause the two polygons to have the same shape. When you start changing angle measurements inside of a polygon, that is what is going to make the difference between a quadrilateral being a rectangle or being a rhombus, or possibly the difference between being a kite or being a parallelogram. Okay, so corresponding angles are going to have to be congruent, and the second thing is that corresponding sides are going to have to be congruent. And that is what is going to cause us to have the same size. And if you think about it, if two shapes, if you are allowed to change the side lengths on one of the shape, obviously you would be making one of them larger than the other, so you would not have congruent polygons. Okay, so the rest of this discussion is going to be about this, the corresponding angles being congruent, corresponding sides being congruent, but as you can tell, we continue to hear a certain word over and over again, and that is corresponding. Now, we've used this word this year already to mean same basic location, but at different intersections. Well, this definition is mostly going to hold true for what we are doing here today. Okay, so the key is going to be figuring out what corresponds to what. Okay, here are two triangles. Okay, copy them down, including all of the angle measurements and including all of the side lengths. Now, if we are going to state that these two triangles are congruent, which they are, well, there must be reasons for why they are congruent. And of course, we've already said that there are two things that must happen in order to make these two triangles congruent. First, for every side length that is on the red triangle, the figure on the left, there is a corresponding congruent value in the blue triangle on the right. As you can see, the side lengths, there's a 3 on the left, there's a 3 on the right. There's a 4 on the left, there's a 4 on the right. 5 on the left, 5 on the right. Obviously, we have all of our side lengths are congruent from one figure to the next. Also, for every angle measurement in the figure on the left, there is a corresponding congruent value on the right. Obviously, 90 degrees on the left, 90 on the right. 55 on the left, 55 on the right. 35 on the left, 35 on the right. It's really kind of a no-brainer. When they hand us all of the information, all we have to do is just compare one figure to the next. Okay, now the last one was very easy to see, first off, because they did provide us with all of the information. They did not make us solve anything, and on top of that, they also positioned the figures so that they were basically oriented or sitting in exactly the same position. Okay, but what if they were not sitting in the same position? What happens if they take those two triangles and draw them like this? Are these two triangles still congruent? Well, the answer remains the same. For every side length on the left, there's a corresponding congruent value on the right. For every angle measurement on the left, there is a corresponding congruent value on the right. Okay, so the answer is very obviously yes. Okay, I did this basically to prove one simple point. You cannot get in the habit of just saying the left side from one figure is going to correspond to the left side from a figure on the right, or top corresponds to top, or bottom corresponds to bottom. Okay, so it's a little bit different from the discussions that we had back with the transversals, where things corresponded because they were sitting in basically the same positions. Okay, well, the same position is still basically true, but you've got to realize that the figures could be rotated. So we're more looking for locations in one figure that share similar properties as locations in another figure. Okay, now when we are identifying congruent polygons, there is a way that they have to be named. Just like everything else in geometry, we have a rule for how to name them. And the rule is going to be to name them according to which vertices correspond from one figure to the other. So again, remember, they don't correspond because they're sitting in the same positions. They correspond because they have similar properties from one location in one figure to another location in another figure. Okay, so from the two triangles that we have been looking at, okay, when we go to name them, we name them according to which vertices correspond from one figure to the other figure. Okay, so obviously when it comes time to name two polygons as being congruent, okay, we're going to figure out what corresponds to what. Now, it does not matter which vertices you start off with from one figure, but you have to get the corresponding vertex from the other figure. So if you wanted to start with vertex B from the figure on the left, okay, then to figure out what corresponds to vertex B, well, it's going to be vertex Z. And the reason we would pick that is because B is the 90-degree angle, Z is the 90-degree angle. Okay, B is between the 3 and the 4, those two sides that measure 3 and 4. Z is also between the two sides that measure 3 and 4. So it's very clear to see that vertex B from the red triangle corresponds to vertex Z from the blue triangle. Similarly, vertex A would correspond to vertex Y. They're both 35 degrees. They're both in between the sides that measure 4 and 5. And that leaves us with C corresponding to vertex X. And again, because they're both the 55-degree angles, they're both in between the side lengths that measure 3 and 5. Okay, so very easy to decide what corresponds to what in this figure. And then when it comes time to name them, you simply list them off in corresponding orders. Okay, so we could say triangle BAC would be congruent to triangle ZYX. Now, did we have to start off with the B and then go to the A and then go to the C? No, we didn't. But since we picked it in that order for this particular example, then the order for the blue triangle must be Z, Y, X. So again, you can pick it in any order you want for the first polygon, but however you list the vertices for the first polygon, you must list the vertices in exactly the same corresponding order for the second polygon. Okay, so let's look at another type of example here. Name the following, the following two quadrilaterals are congruent. Name them. Okay, well, in order to name them, we have to figure out what corresponds to what. Now, clearly, with a quadrilateral, as we've said, it's going to take all four vertices in order to name the quadrilateral, because you have to list them all when it comes down to naming any type of a polygon. Okay. Well, it does not matter what we start off with. Okay, we can start off with any vertex that we want from one of the figures, and we can go in pretty much any order that we want, but it's typically customary to go to pick a vertex and travel one direction around the polygon. So if you wanted to start off with vertex E, you can. You could call the quadrilateral on the left vertex EFGH, okay, traveling clockwise around the polygon. Or you could call it quadrilateral EHGF, traveling counterclockwise. Okay. Either way, you just definitely wouldn't want to just jump around. So we wouldn't want to call it like quadrilateral EG and then HF. Okay, don't jump around the quadrilateral. Pick a point and then travel kind of in a circular motion around it. Okay, so what would be if we picked quadrilateral EFGH? And honestly, you can't remember how I have it in the notes, but what would vertex E from the figure on the left correspond to in the figure on the right? Which vertex? E would correspond to L. And the reason we know this is because vertex E is in between the sides that have the 1 tick mark and the 2 tick marks. So we would be looking for the same location in the other quadrilateral, which would be vertex L, in between the 1 tick mark and the 2 tick marks. Then if we went from E to F, okay, then we would go from L to what? From L, we would go to M, because F and M are both in between the 2 tick marks and the 3 tick marks. From F, we would go to G, and from M, we would go to J, because they're both in between the 3 tick marks and the 4 tick marks, and that would leave us H and K. So let's see what I actually have here. And I have it exactly in that same order. Quadrilateral EFGH. Again, it does not matter how we write that one down, as long as we pick a point and then kind of travel around it in order. But then we select the exact same vertices that correspond to the figure on the left to the figure on the right. So quadrilateral EFGH would be congruent to quadrilateral LMJK. Okay, now since we know that the vertices of two congruent polygons are going to be listed in a specific order because of what corresponds to what, that enables us to be able to tell what corresponds to what without even seeing the diagrams. Okay, so we're going to start off with a very vague example here. It says pentagon ABCDE is going to be congruent to pentagon FGHIJ. Now we're going to have a series of questions asking us about these two pentagons based upon nothing more than that statement. Okay, so let's just look. What vertex would correspond to vertex C? Well, have a look at the problem. Obviously, vertex C is in the pentagon on the left. So what do you think that would correspond to in the pentagon on the right? Which of the 5 vertices? Vertex C should correspond to vertex H. And the reason that we know this is because vertex C is listed 3rd in the order of the pentagon's vertices. Okay, so it should correspond to whatever else is listed 3rd, should be vertex H. I've got the answers down at the bottom of the screen, so hopefully we'll get them right when we get down there. What corresponds to line segment GH? Well, obviously line segment GH is over in the pentagon on the right. Okay, so where would that correspond in the pentagon on the left? Line segment GH should correspond to line segment BC. The reason being, GH are listed second and third, so it should correspond to whatever else is listed second and third. That would be line segment BC. I'm sure you're probably getting the hang of it. So what angle corresponds to angle ABC? Angle ABC should correspond to angle FGH, because those are the first three vertices for each of the two pentagons. What side corresponds to line segment EA? Now this one's a little bit different because you see on the pentagon on the left, vertex E is listed last and vertex A is listed first. So it almost looks like E is at the end, A is at the beginning, but you have to remember this is a pentagon. It is an enclosed figure, and as you travel around pentagon ABCDE, and if you keep traveling around it, you will get to vertex ABCDE, but then ABCDE again and ABCDE again. So E and A are actually right next to each other in the pentagon. Okay, just because they're listed first and last doesn't mean they're far apart. In the pentagon, they're actually connected by a line segment. So what side does correspond to line segment EA? That should be line segment JF. And lastly, what angle corresponds to angle FJI? Well, angle FJI, that's the first vertex, the last vertex, and the fourth vertex. So it should be the same order, angle AED. There are the 5 answers that went along with these questions. I do believe that is exactly what I said a moment ago on all 5 of these answers. Okay, so hopefully you've gotten a good understanding of the basics for congruent polygons. This is going to become a very important concept as we roll through the rest of geometry this year, so I hope you got a good grasp of it. Again, these are the notes for Tuesday, possibly Wednesday, depending on how the week unfolds, but I do appreciate you finding time to tune in. Sorry that the notes were a little bit long this time, but I'm sure I'll make it up to you later.